All right, here we are again. So tonight we'll be getting back into chapter eight. It's not chapter eight, 14. Chapter 14, which is our first look at regression analysis. So let me just get that open real fast and we'll get started. Now, of course, we've already started to look at it a couple of times, but I just want to go back and make sure that we haven't missed anything before we dive further into it. All right, here we are. There we go. There we go. Okay, so the this chapter does have two parts, and there's also two spreadsheets, it looks like, or at least one. So we've already started to look at 14A. We'll run through it tonight, and then we also would like to get started in B and see what's going on there. And possibly we'll have time to also do the Excel spreadsheets. We'll see. We'll see how it goes. All right, so the ones there's Armand's. Okay. So we might be able to do this one tonight. And then there's also a part two to this. Let's get that open just in case we have time for it. Ah, okay. Oh, I don't see it there. Okay. All right. So let's do this. All right. So just one more time, let's just mention here that the population regression line is written in the following way. So we have y equals, and we have to have Greek letters because it is a population measure, beta 0 plus beta 1x plus epsilon. So it looks just like any other straight line you've ever seen, except for this part, the error term. This is something you don't see most of the time. So you can interpret this beta 0 as the intercept of our regression line, and beta 1 is the slope. But usually when you draw a straight line, like let's say y equals 2x plus 4 or something like that. This is it with something like this, whatever x you choose, you can calculate the exact value of y from this function. So this is sometimes called a deterministic function or deterministic relationship. Dealing with regression analysis, you're dealing with real world data. And so you've got all these different observations. And the bottom line is the relationship between any two variables in the real world is never going to be as precise as what you're seeing up here because other factors can get involved. So if I were to plot the points from my data set, regression line, well, you can see that almost none of the points are right on that line. Almost all of them are either above or below. And so the error term is there to tell us how much a single observation is off from the line, basically. Okay, so this is the, think of this as the predicted value of y from the regression line, and this becomes the actual y. So the vertical distance between them is what we mean by epsilon. Now here it would be epsilon 1 because it goes with x1. All right, you could do, and you'll end up having an error term for every one of these observations. They could be zero if they're right on the line, but most of them are not. Also, the error term could also be negative. This epsilon is above the line, so it's positive, but maybe if you had something like this, here's x2, our predicted y. Vertical distance, we'll call it epsilon 2. And because epsilon is defined as the actual minus the predicted, that means this one is positive, but that also means this one is negative. Now, as it turns out, unless something is terribly wrong with our regression line, these will cancel each other out. Okay, in other words, if you add up all the error terms, it'll add up to zero. Because, in some cases, the point is above the line, some it's below. But on average, all the points are right on the line. Okay. So, in other words, yeah, there's some above, some below, but they'll cancel each other out basically so that the average is zero. Okay. So, um, that's what those error terms are telling us. And again, that's something you don't normally see with a straight line, but this is a little bit of a different situation. This is real world data. Like, in other words, you're not going to see that with calculus. You've got y equals 2x plus 4. That's it. That's the function. End of story. Now, of course, we never, as you know, we never observe the population data. We always use the sample data to come up with our estimates. So we need, along with our population regression line, which I should have labeled, is of course the sample regression line. So we're going to write it like this. Y, little hat on it. It's informally known as Y hat because it looks like a little hat. But that symbol is actually known as the caret. So technically you should call it Y caret, but most people, even serious econometricians, call it Y hat. That's just the standard notation. Yeah, we had a econometrics professor at Fordham in my graduate school days, and Oh, he got his PhD from Harvard. He worked at Bell Labs. He developed a lot of what we're, using in econometrics. He was a heavyweight in the field, and he called it Y hat. So, um, I guess we can call it that too. Then we're going to use, instead of beta, we're going to use B for the intercept and B1, beta 1. And if you notice, the epsilon disappears because when we estimate the line, again, remember, we're taking into account the fact that the average error term is 0. So the equation that we're estimating is this. Okay. So that's what we're going to actually do with our Excel and with our calculators. Okay. So now they're also going to mention here the technique we're using to estimate this line is called ordinary least squares. Now, of course, this implies, as you can guess, that there are other ways of estimating our regression line. But those other techniques are usually reserved for cases where the basic assumptions of regression analysis are being violated. And this is how we can correct for it. So, though there's so many others, but this is the one we always start with. It's the simplest, it's the easiest to estimate, it's the easiest to interpret. But it also is the one with the most assumptions that if they're not correct, we could potentially be misestimating this equation. We're not going to have time to do any of the other techniques in this class. That's just too advanced. That if you wanted to study more about this, you can do that later on in a more advanced class. But here we're just going to do the OLS, ordinary least squares. And that's, usually for most projects, most type of applications, this is perfectly fine. It's just sometimes you get cases where the data is so far off from what we're assuming that we do need other more specialized techniques. Okay, so anyway, so in other words, what are we trying to accomplish here? That again. So let's say again, we have X here, X1 we'll call it. It's our predicted value. So this will be labeled Y1. This will be labeled Y hat 1. Of the OLS is to choose the line that minimizes sum of the squared differences between Y1, or just any Y, we'll call it YI, and YI hat. Okay, now you're probably wondering, why do we have to minimize the sum of the squares, not just the sum? If you just add up all these differences, okay, so that doesn't do us any good. So instead, we want to minimize some of the squared differences between them. Okay, so that's why we have to square it. It seems like an unnecessary step, but the reality is, if we don't, it will just end up with zeros every time. Okay. So anyway, the fact that we're obtaining our regression equation this way is how we know this is the ordinary least squares technique. Okay. Now, This method implies the following equations for B1 and B0. And we started to look at this chart the other day that you could use to reproduce these results. And it looked like a lot of work, didn't it? It did. It's the kind of thing you could do in Excel very quickly and easily, but to do it by hand, it seems like a lot of work. So you can see what's happening here. And, the reasoning behind this is we're not going to go through the derivations or anything, but this is actually the covariance between X and Y divided by the variance of X rather, slope of our OLS line. Okay, well, anyway, so here's Armand's pizza. And actually, let me just see what's in this Armand's number one. Okay, well, here it is right here. We may want to start working on this right away. So, what they're saying, Armand's is a pizza, it's a chain of pizzerias, and they want to know if their quarterly sales depend on this local student population. Yes or no? And if so, how much does the population affect the sales? So in other words, it's not enough to say, yeah, sure, lots of college students eat pizza, but we'd like to know, like, if one more student moves into the neighborhood, what would that do to our sales? Okay, that's where you can find out with regression analysis. So what they're having us do is set up this table and actually, let me just look ahead a little bit. All right, so technically the Excel spreadsheet that we're going to do here doesn't require this, but um, maybe we should give it a shot. The only problem is it's gonna be hard to write those symbols up here. So maybe we'll just look at it and see what's happening here. So in other words, they've told us down here, um, here we have X, the sum is 140. Since there's 10 observations, that means X bar is 14. And then for the y's, the sum is 1300. So that means y bar is 130. So in this column, we're subtracting the mean of x, which is 10 from each of these x's. In this column, we're doing the same thing for the y's. Then here we're multiplying these two columns together and adding them up. And over here, we're simply squaring the differences between xi and x bar and adding them up. So the b, the slope, the slope rather, for the regression line that we're looking for is the ratio of the second to last column to the last one, 2840 over 568, as you can see here. And so the intercept comes from this formula, y bar minus B1, the beta one or B1 rather, that we just estimated, X bar, which is 60. So the equation itself is y hat equals 60 plus 5x. And of course, we're going to do this with Excel in a second. So what exactly does this mean? All right. Well, the thing is, usually set of a regression equation, but not always, not meaningful. Now, here, maybe we can make some sense out of it because the intercept of any straight line tells us the value of y Zero. So maybe what we could do here is think about this 60 as the amount of pizza that we'll sell in dollars when there are no students in the neighborhood. Or in other words, think of it as the sales to non-students. All right. In other words, if you look at all their sales, 60, I think it's thousand quarterly sales. This is in thousands. So this would suggest that um, x equals zero means not no students. So therefore, this would represent quarterly sales. And again, it's in thousands to non-students. And then this is the students, of course, so that each you actually you should check the units whenever you do something like this. Yeah, that's what I thought. The student those numbers are in thousands, all right? They're not single digits. So student population in thousands. So therefore, we can make the case that this is telling me that each additional 1,000 students add. So we multiply that by five. But remember, this is measured in dollars per quarter. Or in other words, $5 each. Okay. So that's how we interpret the slope here. And of course, now that you have this in place, we can make predictions if we need to. Um, and they'll get back to that later on anyway, but I just want to mention it right now. This equation can be used to make predictions. For example, if we want to predict the pizza sales that would result from having, let's say, 220. No, wait, I'm looking at the wrong column. Let's say 30. Let's say next year we think that there'll be 30,000 students. You can plug 30. Now here's where we have to really watch it. 30 means in this equation 30,000 students into the regression equation for x, and the resulting y is our prediction. So in other words, y equals 60 plus 5x. And that leaves us with a prediction to 10. But the Ys are in quarterly cells of thousands. So this means 210 in cells per quarter or quarterly cells. So if you're, let's say that the school, this neighborhood is like the Bronx, let's say, right around Fordham, and the school announces that they're building new dorms. And so next year, the population of students goes up to 30. So we use that, we, the pizzeria owner, say, yes, what's that going to do to my sales? And that shows 210,000 in sales. Okay. Now, of course, we could very well take out our calculators and do all this our hand ourselves, but it's kind of pointless, I think, um, because all we have to do is come in here and we're going to start Like they want us to draw a graph first. Okay, let's do that. Yeah, they want a scatter plot. Okay, they just want a scatter plot. Let's just do it. All right, the one thing you have to watch out with Excel though is that with scatter plots, it typically assumes that your first column is X and your second column is Y. If that's not true, we'll have to make an adjustment. So we'll try it as we can go insert, charts, scatter. And you can see that it worked because you can see that 250 there. Clearly, those are the cells. That is our Y variable. And down here is our X variable. And just to make sure that it's easy to read the graph, what we can do is we can add labels to the axes by choosing the graph. Up here, pick chart design, add chart element, axis titles. We'll start with primary horizontal. So I'm going to put it like that. That's a way you can indicate. Actually, I think I'll put a little S here.
Professor,
Yes.
I don't have the chart design tab. Am I missing
Oh, you
something?
know why? No, it's one of those weird things about Excel. You have to have selected the
Oh, the data.
chart before it pops up here. You notice how it wasn't there? It's not there right now, if you notice. If you
Yeah.
click it on, all of a sudden, just like magic, there it is. Do you see it now?
Um, Wait, so I need to select the
You
data?
have to select the chart, yes.
Like just like take my cursor and go over it?
Yeah, just click it
Uh,
on.
I'm not. I just see draw.
Oh,
After help at the top, I see draw, not chart design or format.
okay. Are you using a Mac or a PC?
I'm using a Mac.
Ah, okay. This is a PC. Now, the funny thing is I have a Mac, but not with me. Um, it's surprises me a little bit that it's that different. Usually the two versions are quite close to each other.
Uh,
Um, very surprised. I'll tell you what. This is kind of the least of it to put labels in there. So if you can't do it, you can't do it. Okay. I'm just kind of disappointed, but that it's not where we think it is. Is anyone else using a Mac? Huh, that's weird. You know why I say that? Because when I have my in-person classes and we do Excel in the classroom, I notice just by looking around that most of the students seem to have Macs. Um, But in the classroom, the computer that I have access to is a PC. So that sometimes causes issues because they're not necessarily identical to each other. So I'll tell you what, just maybe later on we'll figure it out. But for now, just that's like the least of our concerns. Okay. So now we're going to do the same thing for the vertical axis. Add chart element, axis titles vertical, and you're going to type cells. Actually, let's do quarterly cells. That's and again, and I'll put it like this, thousands of dollars. Now, the important part though is coming next. Now, I hope this is not going to be a problem on anyone's computer. If you right click any of these points, it should give you a pop-up menu that says add trend line. But that's not enough. What we need to do is come down here and click display equation on chart. So is that working for everyone? Yes. And you notice it looks kind of familiar. That is our regression equation. Okay, well, that was a good start. Now, what do they want us to do next? Yeah, we did. That's what we did. They just have slightly different titles. That's fine. Um, if you want, you can come up here and change this title to Armand's. It looks a little nicer. Okay. Now, I think they're going to want us to do something more advanced, though. Um, let's see where this is going. Okay. All right. I'll tell you what. Let's go back to the right click and until you can do add trend line. There's another option that we should have chosen underneath. We don't want display equation n r squared. Okay. I've got two of them. All right, let's try that again. Okay, I'm going to delete the one I have. And so I'm going to try this again. Trend line, and then click both display equation and R square. Now, this R square measure, which we'll discuss in a second, is an attempt to show us how well the regression line actually models the data. How close are those points on average to that line? The way the measure is defined, it can only go up to one. So we have a 0.9027, which means this equation is actually doing a very good job of explaining the relationship between cells and student population. Now they want to explain to us where this R squared comes from, but in order to make this make sense, we're going to need to draw another diagram. So for this, they're adding one more element to it. They're also going to sneak in here a bar. Okay. So now we've got more distances to look at. And so what they're saying here is that if you were to do this for every x and you square the differences, that becomes y1 minus y bar. This is now y1 hat minus y bar. It's getting really small. You know what? I wonder if I can make it bigger. Hmm. Yeah, I just so you can read it better. So, yeah, I know it's getting crowded with all these symbols, but the thrust of this is what they're getting at here is this. The regression line is used to predict the values of y for each value of x, but y bar could also be used to predict values of y, value of x. It would be very boring. It's just everyone would be assumed to be equal to y bar. And of course, on average, they are. So what's happening up here is that this piece represents an error by the regression line, meaning this is where it goofed. It predicted something that didn't happen. Whereas this lower piece represents the improved prediction by the regression line paired with y bar. So I've used this analogy before, and I don't know if it helps at all, but we're looking at that vertical distance. Let me draw this one more time. So this is an analogy that I came up with, and I don't know if everyone really appreciates it, but I'm sure you're aware that in medicine, everyone has cholesterol in their bloodstream. It's just fat that floats around in your bloodstream, but some of it is actually good for you. I don't know why or how, and some of it is not good for you. So if you think of y1 minus y bar as your total cholesterol, um, then these two, you could think of this as the bad cholesterol, and this is the good cholesterol, because the bad cholesterol is where the regression line has incorrectly forecast your point. But down here we have the gap that explains the difference between the regression line's prediction and the y bar. So they have created this R squared measure by doing the following. Instead of just having these terms we see here, we're going to take the sum of the squares. Also, we're going to have to change the subscript from 1 to I to indicate this is true for all of the points. Okay. So in other words, instead of y and compared with y bar, we've summed it and we've squared it. And so remember, this is total, bad, and this is good. So these all have very interesting names. SST, SS stands for sum of squares, by the way. We have SST, SSR, SSE follow. SSE stands for um, error sum of squares. SSR is regression sum of squares. So this special R square measure that I just mentioned a bit ago, um, this is formally known as the coefficient termination, but it's often informally referred to simply as R squared. And it is defined as the ratio of the good cholesterol, so to speak, over the total. This is the way it's defined. It will always be between 0 and 1. The closer R squared is to 1, the better the regression line fits or explains the data. Okay, let me just clean this up a little. So in other words, let's imagine that you've got multiple regression lines that you're comparing with each other. Let's say, for example, here we want to know if there's a relationship between pizza sales and students. But maybe we're also interested in seeing if national local incomes have an effect on pizza sales. And we may decide that we want to choose one or the other. And that's going to depend on which one fits the data better. So one strategy is to compare them based on their R squared. The one with a higher R squared is the one that we'll keep.
Sorry, what does R squared stand for again?
Oh, okay. It has two equivalent names, coefficient of determination, or R squared, and it's an attempt to capture how well the regression line is explaining our data. Now, that sounds very abstract. Let me show you a couple of graphs so you can see what I'm talking about. Okay. So let's choose a case where the R squared is very high and one where the R squared is very low and see what the differences are. All right, we ready?
Yep.
So let's say on the left, we have R squared is zero point 0.9. So the points are awfully close to that regression line. Now let's say we have over here R squared is zero point 0.1. That line doesn't seem to be explaining that data very well. Most of these points are not even close. And so, in other words, that low R squared means that this is not a terribly good description of what's happening with our data. I would not trust this regression equation to make forecasts. It doesn't seem to work very well.
Thank you.
Sure. All right. You know what? This is something every book, every software package, some books, like if you notice when we did this in our spreadsheet, it comes up with a capital R squared. And I wrote it there too, but the book prefers lowercase r squared. Just be aware that it's the same thing. All right. There's no distinction between these two. And so the formula is right here. SSR over SST. It's 0.9027. Now, we only have the graph. We only have the R 0.9027. We don't have these numbers, although we can get them by, they're going to save that. You know what? There's no sense in keeping you in suspense. I'm going to show it to you now. If you were to use your data analysis tool pack, um, here's what would happen. Now, by the way, I think somebody in the class was unable to download their data analysis tool pack. Um, is that still a problem?
Yeah.
Okay. This is so irritating because it should work no matter what version you have. What was what was the holdup again? It just refused to install?
Uh, the whole was when I installed it, it said I needed access to
That's right.
like
There's
a
some ridiculous
content.
message about, yeah, that's right. So that's the kind of thing that, in the school year, I'd have IT come and look at it and get it straightened out. In fact, when school starts up again, you might be able to go down there and ask them yourself. I don't know exactly where they're located, but there's somebody at the school who you can call and say, please help me with this. And they'll be able to figure out for you how to install it. Now, I don't know if you'll ever need it again because this is stats too, but just in case, you might want to consider calling the IT department and having them work with you. I mean, I don't know, may not even be at school right now, but here's what you would have done. Okay, you come over here. Not sorry, data analysis, regression. Input. Now you got to be careful here to make sure you know which is X and which is Y. Y, X. Make sure you tell it that you're using labels. And let's put this on the next page so it doesn't interfere with what we have here. Oh, sorry, no, that's what. Leave it to where it is. New worksheet apply, and hit OK. And you're going to discover something interesting. Hiding in this massive list of numbers is our regression equation. Right here, actually. Okay. Y, so in other words, this is the equation y equals 60 plus 5x. Now, as far as the r squared goes, if you come over here, you'll see that This is SSE, SSR, and SST. All right, well, as neat as it could be. Let me fix that real fast. Just type it. I like that. The only problem is it might interfere with the calculation. Oh no, I see what they did. All right, so it's fine. SSE, and this is SST. And you notice it's what they're telling us in the slides. 14,200, 15,730. And they also have it right here, the results of the ratio of 14,200 to 15,730 is this number right here. Okay. So they've done that part for you. That's kind of helpful. Wow. Now, here's an interesting twist. This coefficient of determination is actually related to the correlation coefficient between X and Y. How? All right, here's how this works. The correlation between X and Y is found by doing this. You're going to take the sine of the slope, apply that by the square root of R squared. Now, our slope is 5, so this is positive. It's approximately 9027. And so if you take out your calculator, you get it's approximately 0.9501. And that's a very high correlation, of course. Now, you don't really need to do this because Excel has already thought of that for you, although they labeled it kind of strangely. Yeah, this is it right here. They're calling it multiple R. I don't know why, but uh, that's the correlation coefficient. Also, if you notice down here, there's other things here, observations, that's our sample size. Um, Now over here, oh, look at this. We have a t statistic and p-values. Hmm. And then we also have lower and upper 95%. Does this mean that at some point we're going to do some hypothesis test? And the answer is yes. Okay. But we'll get to that in a bit. All right. We don't want to jump the gun too much. So the more deeply you get into this stuff, the more impressed we are with Excel, aren't we? Okay, now, okay, so now we're switching gears here and looking at the assumptions that are being made about our regression line. And, a lot of these are about the error term. The error term can contain a lot of useful information about what we're doing here. So what are we assuming? Number one, epsilon can be treated as a random variable, and that means it has its own probability distribution and moments. So this is what I was saying before. The error terms are going to cancel each other out. On average, there'll be a bunch of positives, a bunch of negatives, but they will ultimately add up to zero. If not, then there's something horribly wrong with our regression equation, and we need to check it out immediately. It's like I don't know. There's sometimes there's little hints. Something's wrong. Like let's say you smell smoke in your kitchen. Something's horribly wrong. It's the same kind of thing. Um, epsilon. Now I did mention that epsilon is a random variable. It's going to have moments, which includes the mean and the variance. The variance of epsilon designated sigma squared and is the same for all x's in the data set. We don't know what it is until we measure it, but we do know we're assuming it's the same for all of them. Three, the values of the error terms are independent of each other. And then number four, the error term is normal. And it reminds us here with mean zero, sigma squared. Okay, now the hypothesis testing. If our regression results are valid, test the following hypothesis. I remember in the regression line for the population, beta 1 is the slope. Let's go back and revisit that. Right, beta 1 is the slope. So you're probably wondering, well, why are we doing this? What is this supposed to prove? Well, if we reject the null hypothesis, then there is a relationship in X and Y. If we fail to reject H0, then of course there is no relationship between X and Y. So again, you're probably wondering why would that be the case? Because a beta 1 of 0 would mean that your scatter plot looks like this. Slope is 0. This is what happens when X and Y are independent of each other. So in other words, if the slope is 0, there's no connection between the variables. So that's why we're checking this out. We're saying, listen, the slope of this regression line, is it 0 or not? If it's not, then we're all set. If it is, though, that means there's a problem. It means we have two variables that are not related to each other, and our regression line is meaningless. So now, the bottom line here is um, we can run a regression on any two variables, and we will get a slope and a intercept. This is true even if X and Y are not related to each other. Way to find out if there is a relationship between X and Y is to run this hypothesis or test. So yes, we have to check and make sure that even though we have results that they make sense. Okay, now how does this test work? Um, so luckily for us, the test statistic is kind of a mess, but we shouldn't need it. Shouldn't need to do it ourselves. So these two, B1 is the one we estimated. The one we just had with Armand's, that B1 was 5. This isn't something new. This is the standard error of B1. And it doesn't look like something we want to get involved with, does it? It does not. Now, I mean, it's understood. I mean, this is a messy process. If we can use Excel, we're going to do it. So yeah, we don't want to do this. So as it turns out, though, oh, and one more thing we do need to know, the critical values plus and minus t alpha over 2 with n minus 2 degrees of freedom. Okay. So in previous chapters, we had n minus 1 degrees of freedom. Now it's n minus 2. All right. Now, of course, we can also use the p-value approach. So what I'm going to do is show you where to find this information in Excel. Okay. So because, you don't want to do this by hand. So let's come over here to our printout with the data analysis toolpack and see what we can find. All right. Well, guess what? We know, oh, by the way, don't forget, this is the slope. So this is B1 and this is B0. Standard error of B1 here. All right, we'll round it off a little bit. It's approximately 8.616. Now, even this wasn't necessary because look, there it was. It was there all along. How do you like that? Now, the critical values are not here, but guess what is here? The p-value. Look. And of course, once you see scientific notation, come on, it's so small. Wait, with the Excel printout, it defaults to an assumption that alpha is 0.05. Okay, so here clearly the p-value is well below alpha, so we reject null. The beta 1 equals 0, except the alternative that it does not. And so what that means then is that there is what we're going to call a statistically significant relationship between X and Y. And that in turn can be interpreted to mean our regression results are valid. Breathe a sigh of relief. So in other words, Armands can use that equation they estimated to forecast accurately the impact of a certain number of students on their cells. Okay. Wow. This is very intense, isn't it? That's true, but you'll get used to it pretty quickly, especially because we don't really have to do a lot of the calculations. We're really more focused now on the interpretations. All right. What's next? Confidence interval. Now, by the way, here's something I do want to point out. When you look at your cell printout, see what it's got here. It has the confidence interval that we need, but for 95%. If you want 99, you have to do something a little different. So let's just copy this first. Now, keep in mind, the top row is for the intercept, which usually we don't pay a lot of attention to. This is what we're after. So the 95% confidence interval for B1, or it's actually beta 1, is what you're seeing here. Let me show you how you would get a different confidence interval. We'll go back to the data analysis tool pack. Out of here. I'm going to run it again, and this time I'll ask for 99. The data. I select my data analysis tool pack, regression. There's only one change right here. You see where it says confidence level? I'm going to type in, you see how it defaulted to 95, 99. Okay, and we're going to ask for a new spreadsheet. Here we go. So here's how they handle it. They always have 95 if you need it. But then you notice how they've added these two. Before, they were both 95s because we didn't tell it to do something different. But here, because we specifically asked for 99, they'll give it to us, but it's listed down here at the end. Okay. So that was pretty straightforward. Remember, all of this is for B1. We almost don't care about these. Oh, you got to even pretend that they're not there. And that's how it's done. All right, and we could have also asked for 90. Right. So, and this is what they're actually doing. Now, if you wanted to, you could confirm that they've done it correctly. Because, whoa, but we have to look this part up. Okay, never mind. All right. But that's what that looks like. That's what they're actually doing. Now, this part, I know they wanted to show it to us, but this really is relevant mainly for multiple regression analysis. We don't really need to do this as well as the t-test. This is the so-called f-test. What is it for? Well, let's briefly take a look. What we ran up here is referred to as the t-test. I'll add that back here. And that's because the test statistic is based on the t-distribution. All right. Yeah, this is one of the risks. Whenever something happens to change the what's on the pages, there's always a risk that the writing gets all mangled up. I have to keep an eye on that. All right, that'll do. The f-test, see, let me show you with multiple regression, the difference is that there's going to be two or more independent variables. Like for example, and so that of course complicates everything, but we'll not be doing that in this chapter. But the point of the f-test is to do this. So it enables us to check all of them at once, all the slopes, which is obviously very efficient. But with simple regression, f-test produce the same results. So I'm kind of surprised to see this mixed in here because you normally you'd think they'd save it for chapter 15, but let's take a look and see what they've got. So with only the one independent variable, what's different is the test statistic. And it says MSR over MSE. What is that supposed to mean? All right, so we're going to go back to Excel now. Table here. Interestingly enough, that's referred to as the ANOVA table, even though we're not actually doing ANOVA here. So what's happening here is that these are my degrees of freedom. These are the SS's. So each, remember, this is SSR, SSE, SST. This is MSR. This is MSE. So MSR is SSR over the degrees of freedom, which is 1. So these are actually equal to each other if you notice. Then we have MSE. So in other words, it's 1530 over 8. Oh, this one at 14,200. 191.25. And that's what you're seeing here. And then the ratio of these two numbers is the F statistic. It's about 74.25, let's say. And, if you really wanted to, you could go look at the critical values we're not even going to use it. The p-value is printed out on Excel. Two 2.5488 7 E minus O 5. Of course, alpha is usually assumed to be 0.05. And that means that the p-value less than alpha. All right, now here's the part that you might find interesting. If you look at this printout again, actually, we need the whole thing. Hold on. Yeah, the p-value for the F test, except for the round. I mean, this one's showing more digits, but if I wind it up, it's the same number. So, like I said, with simple regression, the F test and the T test are giving us the same results. So we don't really need the F test. This is enough. With multiple regression in chapter 15, you would need them both. Okay, Yeah, so that's why I said I'm not sure why they decided to do this, but so what? Oh, okay. They want to nitpick with us a little bit here. Rejecting the null and concluding that the relationship is significant does not necessarily mean that there's a cause and effect relationship. In other words, it may just be that there's some third variable that causes them both to rise or fall at the same time. It doesn't imply necessarily that X causes Y or Y causes X. Okay, but it does show that there's a tendency for them both to move in the same direction. Also, if we're able to reject the null and demonstrate statistical significance, it doesn't guarantee that there's a linear relationship between X and Y. It could be that there's some kind of nonlinear thing going on here that's close enough that we conclude there's a relationship. So imagine if the points look more like something like this. There's kind of a curve going on here. That's what we mean by nonlinear. Remember, regression analysis assumes a linear relationship. So, in other words, what they're saying is you might find yourself rejecting the null, even though it turns out there's not a linear relationship here. So you just have to be careful interpreting your results. Okay. All right. Just don't jump to conclusions, is what they're saying. Sure, if there's any more to this Armand spreadsheet, let me just see what's coming up in B. Armand, I think this is meant for Armand's too. Let's see what this is. All right. So I'll tell you what, it looks like we're done with the first Armand. So why don't you save that and send it over to me? No, this is it. We're good. Hmm. So I'm going to put this away. Now, I realize now what's going on here. These formulas we're about to look at are so, fortunately, it doesn't look like Excel can do them directly, but if we go through all these steps, we can do it ourselves. Let's see what's coming up next. So we're going to have a confidence interval here. We're also going to create something called a prediction value or interval. And we're going to see how they're calculated. Now, the formulas look pretty scary. All right, very scary. So we're going to do these in Excel. Okay. Excel doesn't have this, but we're going to do it anyway. Now, before we do anything else, I'm going to open up my solutions. I just want to remind myself, I want to make sure I haven't overlooked something. All right, so we're gonna go back and sort of capture a lot of these calculations that we glossed over before, and then we're gonna bring it all together into sheet three and come up with our confidence and prediction intervals. Okay, so let's go to Armand number two, and we're gonna start filling in some of these details. So first we need the means. So let's just do average. That's easy. This across because they're both calculated the same way. For x minus x bar, for each x, we're going to subtract the mean of B12, but don't forget the dollar signs because we don't want that reference to change. Once that's done, you can drag it down. Then we do the same thing for y minus y bar. So here we have C12 with dollars. So it looks like what we saw in the slides. Now here we're just literally multiplying columns D and E. Here you're just squaring column D. All right, so I'm gonna do the control tilde thing that lets you see everything at once, just in case you missed one of these. That's how far we got so far. All right, give me a minute to catch up. Yes, so in each of these cases, you only need to do it once. All right, now over on the side are the formulas. We saw these earlier. Now we can actually put them together ourselves. It's a little annoying, but it's not too bad. In fact, B1 is nothing but the sum of column F over column G. Zero is Y bar minus the product of this B1 times X bar. That's it. Now, I'm in the mood to show you another shortcut. Um, Watch how simple this could be. In Excel, the formula for finding the slope is just called slope, as long as you make sure that your y's come first and your x's are second, worked. And then the intercept is actually spelled intercept. It's first. There's so many shortcuts built into Excel. It's unbelievable. So where does that leave us? Oh, now we're going to come up with our um, test statistic and critical values. So y hat is the result of plugging in this x for into this equation that we've estimated. So it'll be 15 with dollars plus B 14 with dollars times X. Whoops, no parentheses there. Times X. All right, let me make that a little bigger here. That's the value predicted by the regression line for any given value of X. Drag it down. Okay. Just, I'm going to take a look at my solutions and make sure that nothing got goofed up. Then this one is just the square of column H. And oh, y hat minus y bar. All right, we don't have that one yet. This is y hat. Y bar is this one, C12 with a dollar sign squared. And then here we're literally just squaring. This is something completely new. This is just y minus y bar. Okay. So that's going to be, oh, it's already there. No, it's e squared. Okay. E2 squared. That's better. Now we need sums down here, so I'm just going to drag this across. Oh, that was fast. All right, now n is the number of observations. We can just go to count, go back to the x's and y's. And that's 10. Now these formulas are sitting right here. SSR is the sum of the y hat minus y bar squared, which is this one. SSE is y minus y hat squared. Okay, that would be, wow, that looks awfully large. Hold on 1 second. No, I knew something was wrong. Hold on, this one is off. Oh no, that what did I do? That's not correct. It was supposed to be oh, I screwed it up. Sorry, it's C2 minus H2 squared. Sorry about that. All right, let me show that to you one more time. And then you can just drag it down. Everything will be okay then. Okay, drag it down. So SSE is that sum. SST is the sum of column K. As we saw earlier, R squared is the ratio of SSR over SST. Now, what is this S squared doing here? This is something we kind of glossed over it before. This is called, let's see, let me make sure I'm using the correct terminology here. Standard error of the estimate. Okay, let's make this into the notes. Now, what is it for? This is the estimated value of the common standard deviation of all the error terms. And it's often the standard deviation is written sigma, but S is its estimated value. So let's do this in the spreadsheet. And let me show you where it's found in Excel. Hmm. So it's the square root, says E, divided by N minus 2. Oh, sorry, I just realized, no, that's, we don't need the square root there because they're asking there for S squared, and then we're going to square root it. That's what we're going to get. Now, by the way, when we ran this regression in part one, which I guess it's right here in Excel. And it actually says standard error 13.829 something. Okay. so much more. Let's see, the formula for B. So, there it is. Okay. So it's this one over this one. Now, this is not the intercept. This is the standard error. This disastrous thing here. So you'll find that one. It's L21. L21. It's S over the square root of over here, X minus, oh, there it is. All right, L21 over the square root of G12. And if you'll recognize that because if you come back over here to the Armands, number one, oh, I put it away again. Oh, that's this number right here. Okay. The standard error of B1. All right, now let's get back to this one. T, the T statistic is B1 over SB1. So you're going to have the ratio of these two. Degrees of freedom is n minus 2. The critical value, there's a special formula for that. Let me just go look it up real fast. It's T INV two tails. 6. I spelled it wrong. Yeah, oh, I got it out of order. T dot INV dot 2T. And then confidence interval is here. Okay. B1. Oh, all right, we're gonna do B1 minus T times SB1. Okay, there we go. It was L23, which is B1, minus, so here we've got the T statistic, L28. Sorry, the critical value times SB1. And this one will be the same thing, only plus. L23 plus L28 times L24. And again, you can find this directly on the Excel spreadsheet. That's what we just reproduced. All right, so that one's done. Now over here, a lot of this stuff is already in place. It's already done. All right. The y hat, yeah, the predicted value. This is the interval. This is the confidence interval for y hat. This is the prediction interval. Okay. Or at least this is the standard error. This is the confidence interval. This is the prediction interval. Here I just put it all in there because it's such a mess. But this way you have something to look at. If you run into this on MindTap, you've got something to lean on. All right. Let's see. Now here they're finally getting around to showing us how to do this in Excel, which is nice of them. Now, what's happening here is that remember before all the assumptions of regression analysis are based, it appears on epsilon. So with sample data called a residual, which is an estimate of an error term. Or think of it as the sample version of the error term, which comes from the population. And it's written in a very special way. Also, I just want to point out, I don't know if this book does this or not, but if you have epsilon for an error term, often you'll see the Roman E used for a residual. And if that's the case, residual for observation I is yi minus yi hat. So because the assumptions are all heavily based on the errors, the residuals can give us a lot of information about whether or not our assumptions are being met. By the way, we're done with this second Armand spreadsheet, so you can go ahead and send it over here. Um, yeah, luckily for us, the worst page is already done for us. You can go look at it and see if you want to use it for your assignments, but it's done, so you can send it over here.
Sorry, could you show the critical value formula one more time?
You're missing something?
Yeah.
All right, let's take a look. What are we looking for?
The on sheet two, the critical value formula.
Oh, yeah, here it is.
Okay, thank you.
It's a very unusual command. Anything else?
That's all. Thank you.
Okay, good. All right, well, that was a nightmare. But you know what? At least, like I said, you could actually use this as a template for problems that show up in MindTap if you needed them. Now, I would like to point out that we could have done if we put the data into the lists, the calculator also has some capabilities of doing regression analysis. But we're not, just want to see how much further we have before we're done with this chapter. But next time I can show you how we would work with your calculator. It doesn't maybe show as much information, but it does a good job. So anyway, that's where this is heading. So what's often done is that you plot out the residuals against X to see what pattern forms, if any. And so when you're to tell whether your model is, valid or not, if we plot residuals against X, you're going to get whoops, some kind of a pattern. Now, ideally, what we want is just a random jumbling of points. Okay. Where it's clear that half are above the zero line and half are below. If we have patterns, that means our assumptions are probably being violated. For example, let's say that most of the residuals are above the line. Okay, this means there's a problem with our data. Or the residuals. So in other words, the violations are being assumption. The assumptions are being violated. Hold on. And then, there's a lot of techniques we can use to try to correct for that. But that, right now we just want to recognize when there's a problem. A possibility is that they're evenly spread across the top and the bottom, but there's some pattern of some kind which clearly indicates that there's a correlation between these points. They're supposed to be independent. And that's also bad news. Okay. So in other words, we want to see the points just randomly looking. It looks like when you open up, it's like a soda and all the bubbles come out. Here, you can see there's clearly something going on where more residuals are positive than negative, which is not what we want. And down here, we see a pattern which indicates that they're not independent as they should be. Stop what we're doing and we investigate. But we're not going to have time to get that deeply into this in this course. But if you were to, oh, here we go. They've got some interesting ones of their own. This means the variances are not equal to each other as they're supposed to be. But yes, that would be something you do in a more advanced course, learn what to do about these problems. Oh, that's a really wacky one. That means that you don't even have a linear relationship. That's really bad news. Although there are ways to get around this. I mean, there's ways to get around all of them, but you have to know that they're there to fix them. So what they did here was they went ahead and calculated the residuals for Armand, plotted them. You can see it looks pretty good. And then there, oh yeah, and by the way, in Excel, when you run the regression, one of the boxes that you can click is for a residual plot. So you can see what they look like. We didn't do that, but maybe next time. All right. So I'll tell you what, here's what we're going to do. We'll stop it right here. We've gotten an awful lot done here. So I'm going to remember make a recording for the weekend because of Tuesday. And what I might do is come back here and revisit some of this stuff, but I'm also going to move on to the reviewing for the second sample midterm, which is chapters 11 and 12. And then when that's done, we're going to look at the sample final for 13 and 14. So um, we're getting awfully close to the end here. So uh, I mentioned it last night that the exams are actually in there if you want to start them. Just quickly show you where to look. Don't forget, even though you only get one chance at each question, you still can do it in stages. You can do a little bit here, a little bit there, save your results. Um, that hasn't changed. All right. So, oh yeah, quite a few. Oh, some people have already tried the final. Look at these averages. I'm very impressed, especially since you only get one chance at it. Wow, that's pretty amazing. I love it. All right, so I guess we'll stop, and then so I'll send out the video over the weekend, and then Monday, we'll just wrap up whatever still needs to be done, and maybe. So the thing is, we may not need to meet. In fact, we probably won't need to meet every time next week. It's possible that Monday or Tuesday will be our last session, but even if it is, I'll be available for Zoom sessions if you need extra help. And so that way, you haven't been abandoned or anything, but we're almost done with everything. So we won't need to keep having these sessions at 6 o'clock, but we can still do reviewing if you want. Okay. And so the due dates for these exams are on the 3rd. I think the grades are due like maybe the 6th or so. But if you finish early, I can get your grade in there sooner. So also, you may have vacation planned and all this and that, and you want to wrap it up sooner rather than later, and that's fine. All right. So, but for now, I guess we're done. And I'll see you on Monday for sure, and then we'll play it by ear after that. Okay. All right. So I turned this down just so it wouldn't get in the way. So I'll see you all next time.
Thank
I had a
you.
quick
Thank
Okay.
you.
Bye.
question
Okay.
for the midterm and final. Just checking. Is there like a time limit once we
No,
start?
there's no time limit. No, it's just like the other
So we
midterm.
next month.
It's like all the mind tabs except you only get one try instead of three.
Okay, sounds good. Thank you.
So if you want, you can spend an hour on each question if you want to.
Okay, awesome. Thank you
Okay.
so much.
All right. All right. See you next time.
Excuse me.
Yes.
Hi. I was able to finish the midterms and the final. Um,
Oh my God. Well, then you're done with the course.
okay, that's what I was gonna ask because I just emailed you the Armand. So as long as I've emailed you all those Excel sheets, I've done all the work in Cengage and all the midterms and finals. Then I'm fully done.
That's exactly right. You're done.
Okay. And so it seemed like you pretty much covered all of 14B today. So,
Yes, it's pretty much done. There's almost nothing left. So if you're really done, I mean, you don't even have to watch the videos or even show up
okay.
next Monday. You're
Okay.
really and truly done with everything.
Okay. And you said not to rush you at all, but you said you'd be able to put the grades in faster.
Yes, but it probably would have to wait till at least the weekend.
Yeah, no worries. I'm not
Okay,
stressed.
oh, okay, yeah. So what I'll do is I'll sit down and start looking at them, and if I start to see people who are completely done, then I'll start putting them together, and you may not be the only one. But
Okay.
if you're really in a hurry for some reason, you can send me an email, and I'll speed it up a little.
All right. Well, yeah,
If in fact you
no, it's
probably
no
should, I'll
rush.
tell you why. By the time I get home tonight, I will probably have forgotten all about this conversation.
Yeah.
Um, So just send me an email and say, I don't want to be pushy, but could you, grade mine as soon as you can, and I'll take
Okay.
care of it.
All right. Thank you so much.
Okay, you're welcome.
All right.
So bye. All right. Anyone else? All right. See you next time.